Let's get started. So today we're going to finish up our unit on probabilistic modeling. And since we're a little bit behind from the last one, I decided to break it up the following way. I decided to go over in some detail Bayesian modeling, which is actually going to be the majority of the lecture probably, and then talk a little bit about deep generative networks. So originally we started thinking about maybe having a lecture on deep generative networks, but I think instead we'll just kind of give a brief overview and hopefully a highlight to related work that you guys can look at if you're curious about kind of the state of the art here, because it is very impressive. Before I begin, though, a few comments in general. First of all, the third homework should be out tomorrow night. Again, I mean, sometimes we get slack by a day or so. This time it will be just 2 weeks, so you will have 2 weeks from where we assign it that it'll be due. But it should be there tomorrow night at 12 or the following day at 12. I think that the other thing I wanted to mention was about the project feedback. So some of you have already gotten feedback. Actually, everyone in Ariel's bundle, he's a little bit more on top of this than I am. So everyone of his got feedback. I'm still sending them out. I'm sending them out in a big batch, so they're almost done. I'll send them out tonight or tomorrow morning. And I think the biggest comment I have is I think in response to the comments I said last time, where I mentioned the fact that people should be citing previous work and thinking about what the previous work is. The most common thing we saw was that people would write a proposal and then cite a bunch of things, but not actually say how they would build upon that, right? They just said, we're going to do this, and look, here's a bunch of papers that also do that, which is not really the point. The point is to think about how you can actually either implement or build upon this previous work. So I mean, not everyone did this certainly, but the majority of comments I think are along those lines, and that I'm going to want people to be a little more specific about how they're going to build on previous work, and sort of what elements from previous work if any, you are taking. And again, it's fine to just have your project be taking some algorithm people have proposed and implementing it on a new data set or testing it in some new regime. That's perfectly okay. And in fact, it's much better to do that than it is to just sort of start anew without recognizing that there has been past work on this, or acknowledge the past work but don't really address it. So that's the main comment I have of the ones, but I'm going to provide feedback. It's going to be relatively short, a couple sentences, but going to send that feedback out tonight or tomorrow. Any questions on that? And then there's the deadline, and somewhere in the class notes, class website is for the next deadline rather is for the midterm, the midway report. Any questions on that? Okay, so in that case, let's move right on to Bayesian modeling, which is going to be the majority of this lecture. Again, these two topics, both Bayesian modeling and deep generative networks, are, of course, like many things in this course, themselves very, very long topics we can spend a lot of time covering. But I'm going to try to give you a brief overview of these things to the point where you sort of understand the basic ideas here, if maybe not all the details, certainly. So to talk about Bayesian modeling, I want to come back to maximum likelihood estimation. And the core idea of maximum likelihood estimation is that we essentially have these two groups of things. We have variables and we have parameters. So variables were things like x, right? They were things, or maybe y in a classification task, right? They're the random variables that we actually observe in our training set then. And parameters were the things that we fit to the data to sort of describe the data with certain distribution. And so the way we wrote the kind of canonical maximum likelihood estimation problem was that we wanted to maximize over our parameters, theta, the sum of log likelihoods of our data points where the probability of each one is parameterized by this parameter theta, right? And that was kind of the core idea of MLE, and it really also formed a lot of the foundation for machine learning, because a lot of times in machine learning, our loss function is exactly that probability there. So I want to propose an alternative view now, which is the Bayesian view of this thing. And in the Bayesian view, everything, including our parameters, our old parameters, what we call our old parameters, theta, is now actually going to be a random variable. So we're no longer going to talk about estimating our parameters as much as we're going to talk about come up with a distribution of our parameters, right? And the way I'm going to sort of denote that notationally is that instead of this notation, if P of x parameterized by theta, or it could be right. It could also be P of y given x parameterized by theta, or it could be P of x parameterized by theta, depending on whether or not you were in a classification or regression setting, or whether you're just in a generative model or in trying to model your data setting. But we're going to move from this essentially to different notation, and we're going to call this now P of x given theta. And this is just going to emphasize the fact that now we're thinking of theta itself as a random variable. Before theta was just going to be a fixed point, but now theta was going to be a random variable. And so in order for these things to have meaning, these probabilities here, we also need to ascribe some notion of distribution over possible parameters of theta. And the way we're going to do that is we're going to think about an idea called a prior distribution. Which we're going to write as P of theta. And I will drop this soon because it gets kind of cumbersome to write. But I'm actually going to also say this has some parameters too, certainly. And I'm going to write those parameters as being alpha. And so now we've kind of shifted the target one step over in effect. And now that theta is going to be considered a random variable, but in order to sort of make that a well-defined probability, we're actually going to need to assign some notion of a distribution over theta. And the way we do that is by assigning assigning distribution of theta parameterized by some parameters. And so we're kind of passing the buck a little bit. But the reality is that those things which are called hyperparameters now, so these things are called hyperparameters. So like the regularization and such in machine learning, these are also referred to as hyperparameters. But the key thing here is that unlike maximum likelihood estimation, we're never really going to worry about estimating these things. We're just going to give some value to them and they'll be considered fixed. And the reality is oftentimes we choose hyperparameters such that the prior distribution over theta is very, very wide. In other words, there isn't a lot. We're sort of, sometimes they're called uninformative priors in the absolute limit of really providing no information. But the core idea is we're not going to actually rely too much on the prior. What we really are going to care about actually is going to be the opposite of this thing. It's going to be the distribution of theta given our parameters. So once we have this thing, once we have sort of this, and now we have this, our old likelihood is now going to be written this way, which is going to be the same thing. So for example, if we had a logistic model, P of x given theta would actually be the same functional form as P of x parameterized by theta, but we're just going to think of theta as being a random variable here instead of being a fixed parameter. And we're going to combine it with this prior distribution term. And so now the central question of Bayesian statistics really is trying to come up with what's called a posterior distribution over your parameters. Remember, this is now a random variable. And so sort of in some sense, the key question of Bayesian statistics is coming up with a distribution of what is my distribution over my parameters given my data. Right? And that's going to be kind of the central question we're going to actually deal with here. And it turns out, fortunately, of course, we can just write this with Bayes' rule. So in general, this is just going to be, well, let's just write this using Bayes' rule. This is going to be P of x given theta, P of theta, and this is, remember, our prior distribution over the integral over all theta of P of x. I may also just say like theta prime, P of x given theta prime, P theta prime parameterized by alpha. Okay, and d theta prime. And I'll come to an example of this in a second, which will hopefully make it a little more clear, but that's sort of the basic idea. So again, this is actually much more of a kind of, so far I haven't really talked about sort of algorithmically what this actually means yet. It's more of a philosophical thing. The philosophy is saying that we don't think, or we're not going to try to find any single parameter that's going to best describe our data. Instead, we're going to have some prior distribution over our parameters, which may be a very wide distribution, but it's going to be a distribution of our parameters. And we're going to then try to come up with a distribution over our parameters after we've observed the data. In other words, the posterior distribution of theta given our observed data x. And I guess I'm writing a big X here just to indicate this is in fact going to be all our data, right? So if we have a bunch of samples, this would in fact be the entire set of samples here. Okay. So are there any questions so far? This is all very conceptual so far, I know. It hopefully will be a little bit more concrete on the next slide. But this is the basic idea of Bayesian statistics here. Yeah?
I understand why you don't point, like, but why chose it as a
Why should you do this as a random variable? This is sort of one of actually the classic like philosophical questions of statistics, right? Is this Bayesian versus frequentist modes? This is actually, if you ever heard that distinction, the Bayesian setting versus the frequentist setting, this is actually exactly what it's about. It's about, do you try to find a point estimate of your parameter? I mean, there are other aspects of it as well, but do you assume that there is some sort of underlying true distribution? You just try to find the best estimate of that as you can? Or do you say, what I really want to do is sort of quantify the uncertainty I have over my distributions, right? Because really this gives us a distribution over all the possible thetas, which themselves then prescribe distributions over our random variables, right? So this is much more about, rather than trying to say, I'm going to pick a fixed kind of value that I'm going to commit to. This is trying to say I'm just going to come up with my sort of estimate of my uncertainty over my parameters. So in some sense, it's kind of a philosophical difference, though. And again, this is not really these philosophical debates are definitely not my forte, because people argue them with a subtlety that sometimes actually I don't really understand why they're so emphatic about these things. But when you talk with statisticians, they will be very, very emphatic about this, about what is the correct kind of philosophical way to approach uncertainty in the world. Do we approach it as trying to say that there's some true thing that we're just trying to estimate? Or do we approach it saying, let's try to estimate our distribution over our uncertainty? And so there are sort of practical implications of this, and that's largely what I'll focus on here. But there are also deep underlying philosophical distinctions that I will not touch on, that statisticians will debate for hours about and not get any closer to a resolution. Including people here, by the way. There have been some from some statisticians. So Larry Wasserman used to have a blog and got into like a really heated discussion with a Bayesian statistician over whether or not a certain type of result would hold or essentially doesn't work in a Bayesian setting versus working in a frequentist setting. And there are really, really heated debates that I don't really pay much attention to personally, but there is this whole sort of large philosophical debate going on here that I'm glossing over entirely. Yeah, and in my lecture, it's just basically a matter of whether you use a bar or a semicolon. That's sort of the extent of my philosophical stance there. Okay, so let's say this actually works, because I think this will be a lot more clear if we talk about an actual regression or an actual applied setting here. So the context I'm going to use is something called Bayesian linear regression. So if you remember linear regression, it's sort of the canonical machine learning algorithm. But as I mentioned also, you can kind of think of it as a probabilistic model where your observations, that is the y, your output as the y, given your parameters, or rather given your input and parameterized by theta, would be some normal distribution, the second line basically, normal distribution of with mean theta transpose x and some covariance there. That was actually a way we could describe a probabilistic model behind linear regression. So I'm going to sort of take the Bayesian view now, and I'm going to actually describe a version of linear regression that will actually give us a full distribution over our resulting parameter theta, rather than just a point estimate of theta. So you remember linear regression, right? We had a bunch of x's and y's, y1 through m, which we also, by the way, sort of described as a big matrix x and a big matrix y. And we said that theta star, which we know is actually the maximum likelihood estimate of theta given a Gaussian observation model, this is going to be equal to this set of normal equations here, x transpose y, right? And this is actually a point estimate of the optimal theta under a certain probabilistic model. Namely, our model here was that y given x and parameterized by theta is distributed according to normal distribution with mean theta transpose x and covariance sigma squared. Though it turns out that sigma squared actually doesn't appear anywhere here. It doesn't actually matter for your optimal estimate of theta. If that's a little bit fuzzy, or if I didn't quite cover that in that much detail in class, don't worry. That's just sort of a fact that we're going to use, but actually we're going to basically rederive a more general thing right now anyway. Okay, so this is and this, I should say that all this in some sense is kind of the frequentist view of linear regression, right? It's the standard maximum likelihood estimation view of linear regression. So now I want to actually go instead with the Bayesian view and see what that looks like. And so in the Bayesian view, we no longer are trying to find a single estimate of this. We're going to try to instead find a distribution of our parameters given the data we observe. And so in our case, the way we're going to do that is we're going to ascribe first a prior distribution. So we're going to assume that theta here itself, this is sort of the normal distribution. This is the prior distribution of theta, is normal with mean 0 and some covariance rho I. And then we have the same model as there before. So then given that, y given x and theta is going to be normal with mean theta transpose x and covariance sigma squared. Right. Does that sort of setup make sense to everyone? Again, the way you can view this is as a generative model, right? So what this is saying is the way we generate our data is we first sample a theta according to some normal distribution with this distribution. So we sample our parameters according to that. And then, given our parameters and given x, and we're actually not going to ascribe any probability to x itself. We're just going to assume that we're still given x. We're not going to sort of assume that has a generative model behind it either. We're just going to assume that this one is a random variable. This is just some fixed observation we have. But given these two things, then y is going to be normally distributed with this mean and some sigma squared variance. And that's going to be our sort of generative model story for how we construct our data, which again, that's not how real data is constructed usually, but that's going to be our mind's model of how we go about building a set of y's for a given set of x's. Yeah.
Yes, so it's not very clear with according to the practical data set. So if we take those x's and y's from practice, those say that like the model will not be close.
Right. So that's actually a great point. So the point here, and I think it's actually a really good one when it comes to Bayesian modeling in general, but also MLE, also statistical modeling in general, is that the generative process that describes the model is not necessarily what you think of as the thing that really produces your observed data. What you're really going to do is you're going to say that what we really care about is not going to be sort of the fact that our generative process gives us data that looks just like the real thing. But the closer you can get to that, kind of the better off you are. What's really going to matter, though, is the posterior distribution. So once we've observed a given set of, essentially, in this case, it's going to be y's and x's, what's our distribution of theta going to be? And that will still convey some sense of the uncertainty we have over theta if you think this is, maybe if you don't believe this model, at least if you sort of think that it's a reasonable way in which data could be generated. And again, not for a particular problem, but for sort of the space of all linear regression problems. If you think it's sort of generally like this, like, if you looked at every single paper that creates a linear regression model, and somehow these are all, the distribution over your parameters here might look something like a Gaussian distribution. One instance then of your problem would have a concentrated mass around a single sort of set of points, or a certain region of the state space when it comes to theta. But it's still, what's really useful here is the posterior distribution over theta, given your observations, not really the prior distribution sort of as it is. I know that's a little bit sort of. So if that made things more complicated, don't worry, because I know that it's a little bit convoluted, but hopefully it was helpful to those that are sort of thinking the same thing. Yeah?
Do people generally do some sort of analysis where you're looking at the posterior distribution, trying to change your theta model such that probably the posterior is in high variance, or?
Yeah, so what I'll say is, in general probabilistic modeling, it is very common to try to tweak your generative model such that samples, sort of naive samples from your model, look more like the data you actually observe, right? So the more that's the case, sort of the more you believe your prior in some sense for your given problem, right? Because the more the data just sampled randomly from this process here looks like the data you have, the better. I mean, a similar thing comes up with these topic modeling models, right? Which, again, I didn't really cover in too much detail. We won't have time to go into them too much. But they are all what are called bag of words models. in that the text that it thinks the way it thinks the document is generated is that you pick a random word out of a bag and throw that word in the document and you repeat this process. So real documents don't look like that, right? But yet the posterior distribution is still very useful. However, there are more complex models where people actually think about a language model that tries to generate the words, sentence, word by word that actually makes sense. And oftentimes you'll have much more complex prior models that actually incorporate a language model. The flip side is the inference is often harder in these models, but if you can do inference, you often get better results because your prior model does actually look more like the data than just these sort of random models. But the big point I would emphasize here is that even though this generative process seems extremely extremely unlikely to generate data that actually looks like your given instance, even when that's the case, as it is in this model, as it is in LDA models, as it is in most typical generative models, the posterior can still be very informative because essentially what that's saying is what are the parameters I would have needed or distribution of parameters I would have needed to make my data actually occur this way, and that can still be very informative. All right, so what I'm going to claim now, I'm going to claim with this model that the posterior now of theta given x and y is actually, in this case, and this is one of the few cases you can actually come up with a closed form for that big thing up there. But in this case, this distribution here, the posterior, given some observations, and again, I'm going to be a little bit, I'm going to sort of assume my observations here, from now on, x and y are going to refer actually to sort of sets of observations for the most part. But the posterior over these things is actually also going to be normally distributed with some mean and some covariance. Again, this is a multivariate normal distribution because this is a vector in Rn. And so this is going to be a multivariate normal distribution with some mean and some covariance where the mean and covariance are given by those formula. By the way, there actually was a typo in an earlier version. I didn't have 1 over sigma squared there. I just had sigma squared. So download the latest version to get the correct one. But this I'm claiming this is the posterior distribution over my parameters theta. So before I get into why that's the case, I want to make sure that sort of what's being said here makes sense. So what's being said here is that I have this generative model for how I create my essentially labels for my data. I sample some theta, and then given that theta and a x value, I sample my value y according to that process. What I'm saying here is that now, if I look at some given data, so given sets of x, y pairs, and I say, what's the distribution over theta what's the posterior distribution over theta that this data implies? It's this distribution here. Theta itself is normally distributed with this mean and this variance. And we'll talk in a second about where these things came from, but I want to sort of make sure that that basic idea is understood. Any questions about that?
X are given.
X are given. Yeah, X here actually are always given. X, there's no we're not considering distribution over X here. They're always given.
You don't have the true labels.
Right. So the generative model says this is how we come up with the labels. The labels are given by some distribution. Then when you actually are given data, you observe what the labels are, and I try to infer what's the distribution over my parameters given that those x's, but then also those y's. Yeah?
So you can still find a point estimate for the theta, right? More than
Yeah, so you could, if you wanted a point estimate, a natural estimate would be that thing right there, which is the mean of that distribution, right? If I had to pick a single point, it would probably be that thing. That thing, by the way, in the limit of the prior row going to 0, row going to row being infinite, and that thing actually will be exactly the least squares estimate. You can verify that. That's not an accident. I mean, of course, it has to be that. Otherwise, it would be a really bad estimate. But I guess the thing I would emphasize is that a Bayesian would be, aghast at the idea of trying to think about a point estimate from the distribution, because what you care about is not a point estimate, right? It's actually the distribution over theta. So you shouldn't. The idea here is that you shouldn't try to collapse your information about theta into a single point. You should try to actually preserve the fact that there is uncertainty over your parameters, and you should sort of accept that fact. And appreciate the fact that you actually have a distribution over your parameters, not a single point estimate. But if you had to have one, yes, the mean's not a bad one. And by the way, the mean there is the least squares estimate, as your prior goes to a flat prior. And it's actually just a regularized least squares estimate as you have when you have a non-zero prior. So these are all very connected, but they're subtly different. Yeah. Yeah, so it actually can be. So in Bayesian statistics, it's very common to actually take the limit as the prior goes to infinity, and you can actually sort of plug in what this means in this case here. So what this means here is you have this you have a distribution with still has some uncertainty. That essentially that first term goes to 0 because you're taking the limit as rho becomes a really, really high variance essentially. And that still is a that still is a that is not a zero variance. That is an actual variance, and that or covariance in this case, and that means that there actually is some uncertainty over your parameters. That even though your prior may be uninformative, you still have some notion of uncertainty over your observations, over your parameters, and that actually comes from the fact that you also have uncertainty over your observations too, right? So your observations are also uncertain. They are in fact Gaussian with some noise sigma squared. They're not sort of a deterministic function of your parameters, and so you do have uncertainty over that. It is true actually that if let's see, if sigma squared goes to 0 there, then you would essentially have a point estimate of your parameters, right? Because then you get 1 over 0, so that's really, really big. Sigma is the inverse of that, so it's really, really small. And so you actually would have, if your observations have 0 variance, you will essentially get a point estimate, then it's just all a deterministic process, and so it wouldn't really matter. But there definitely is a distribution here, even when your prior flattens out entirely. Yeah?
If we have this uncertainty, how do we use it in real world?
That's a great question also. So what does this really mean in some sense? I'm actually not going to get into this too much here, but what it really means is that when you have this uncertainty, maybe I should have actually done this, but oh well, it's too late now. If I have a new data point now, I want to predict what is my output first on some new x prime given theta. Then actually I will have in this case actually this will be a different estimate if I have any uncertainty over my distribution than it would be otherwise. So this thing will actually incorporate both my uncertainty over over the observations I get there, that's just a sigma squared thing, as well as my uncertainty over my parameters. So if I have a lot of uncertainty here, I'll actually have a very wide distribution here, even though maybe sigma squared there is small. If I have still a very wide prior, I'll still have a lot of uncertainty over my predictions. So the way this can be used essentially is to understand when you're making a prediction, what's the uncertainty over your prediction that you have, sort of irrespective of maybe the variance you see in your point estimate, irrespective of the variance you give in your measurements here, because you might have some uncertainty in your parameters as well. And in fact, actually, in this case, this is which is called the observation distribution or something like this. It's called a lot of things, but this one's also a Gaussian in this case. I don't have it on the slides here, but if people are curious, I'm happy to sort of maybe follow up with some notes on that as well. I can make a post about that if it actually clarifies things. I think I won't write it right now because there's a good chance I'll mess up one of the orders of the things and then have something bad on the board, but I can post that on Piazza if people are curious. For now, I'll just consider the distribution of the parameters. Okay, so how do you show this? Again, the the real math here is not the point I want to emphasize. The point I want to emphasize is more sort of the process about why on earth you end up having this posterior also be a Gaussian and how you show that. And it's actually not that hard to show in this case, in the Gaussian case. So the basic idea here, and I'll just go through the proof in some relatively high, at a relatively high level here. Maybe I'll even bring this down because it's actually the first line of the proof. All right, so we're trying to compute this thing, right? The posterior, the probability of our parameters given our data. And so in that case, what this really is it's that first line there. It's the probability of all my y's given given all my x's. I mean, I'm using Bayes' rule to basically rewrite that thing, swapping the order of the y terms and the theta terms. So I have that whole expression there. That's the Bayes' rule definition of my posterior. And actually, that line there holds for any distribution at all. That's just the definition of these probabilities. So now I'm going to do something kind of clever or obvious. I don't know, depending how you think of these things. But that thing seems really hard to compute, right? And it seems hard to compute in particular because this integral is really nasty. It's an integral over a density that involves, a continuous random variable theta now. So that's going to be an n-dimensional integral in, an integral n-dimensional space there. And we're integrating over all possible settings of theta. What's the probability of my observation given that, right? So that seems really hard to compute what that integral is. We actually can compute it in the case of a Gaussian. You can compute the Gaussian multidimensional integrals, but I'm actually going to take a simpler view here. And I'm just going to say, I'm just going to observe the fact that actually this is a constant for, as far as my distribution over theta goes, this is just a constant, right? Because it doesn't actually involve theta at all. So given theta, that term below is actually a constant value. So I'm just going to call it all C1 and ignore it for the most part. And the reason why I can do this, by the way, is that I'm going to eventually manipulate this density here into a form that I know has to have a certain other normalizing constant. And that's sort of why I can do this. Normally, in general sort of Bayesian estimation, you can't just throw this away. You have to acknowledge the fact that this actually is a term you need to compute. But fortunately, in this one case, I can throw it away. And hopefully, it'll become obvious why I can throw it away later. So this equals, in the case, and again, it's not quite the same as this because I have x's and y's here. But this thing, which in this case is x and y, this equals, in the linear regression case, just some constant times the probability of y 1 to m given x 1 to m theta and the prior on theta. I'm ignoring here my hyperparameters. Those would be the rho and sigma squared. But they're there, actually. If you want to put them there, there should be a colon, semicolon, sigma squared in that first term and a semicolon rho in the second term. Those are the hyperparameters here, but it just gets, the math's already plenty complex without that. So that's actually next I just drop in what those things are. And what I'm doing here is essentially actually being very cavalier with the constant terms in Gaussians. So we know that a Gaussian normal distribution is something like the probability of x is something like, well, it is 1 over square root 2 pi to the n over 2, oh sorry, it's just 2 pi to the n over 2, 2 pi to the n over 2 times the determinant of the covariance matrix to the 1/2 times the exponent of negative 1/2 x minus mu transpose sigma inverse x minus mu. So that's our density of a Gaussian distribution. And so what I'm going to do in those manipulations is I'm basically going to try to get this thing here to look like just the first part, just the second part of this. So I'm going to basically just play a bunch of math tricks. And they're not actually even that hard. They're just basically grouping terms together and then completing a square. But I'm going to play a bunch of tricks to get this expression to look like this. And now, as it's sort of a weird case where I can only do this because I know in the end it actually is Gaussian. So it wouldn't be clear maybe how you would do this if you didn't know it's Gaussian. But basically, because they're all exponentials and they all kind of simplify nicely like this, I can get this thing to look like this, like some constant times this. And then because I know that the posterior is a distribution, right? I actually don't know much about the distribution, but I know that it is a distribution still. It has to integrate to 1 and these kind of things. Then actually, as long as I get it in this form, with some constant times this thing, that I know it actually is a Gaussian distribution with this precise normalizing constant, and that's a term that now integrates to 1 and sort of satisfies all the conditions of a distribution. So all I'm doing here is I'm essentially looking to see how can I rewrite this original form there in this form, the lower form there, and that will tell me then what the mean and variance of my Gaussian distribution are. Okay? So that's actually all that's happening here. It's sort of a very common technique. It goes by a lot of names, like completing the square, but it's really just about some simple algebraic manipulation. Anyway, so how does this work? So basically, I'm going to just start throwing away my constant terms here. What I get is something like another constant times, well, this first one is going to be the exponential of, it would be the sum. I'll write it a little differently than there, but I'll move the sum into the exponential. It'd be something like the exponential of this, and this is a distribution with covariance sigma squared. So this actually looks like, actually that doesn't have to even be a 2 norm there. That could just be this is a scalar of the y minus theta squared xi term. This looks something like this, 1 over 2 sigma squared yi minus theta transpose xi squared times, or maybe plus 1 over 2 rho times this thing. Right, so that's what the expression up there looks like. And now all I do is I just basically group these terms in terms of the matrices we defined before. So remember the matrix form we had of X there was sort of the big matrix X was the matrix where each row was equal to a single Xi. And if I use that kind of terminology, I can actually rewrite this as C2 times the exponential of my thetas here appear both here, and so what I will get is something like this. I'll get theta transpose 1 over, well, put the 1/2 out there just so it's more like that form. Theta transpose 1 over rho I plus the sum from I equals 1 to m of xi transpose times theta plus theta transpose, sorry, there's a 1 over sigma squared here, plus, well, it will end up being something like 1 over 2 minus 2 times 1 over 2 sigma squared, sum over all I from 1 to m, xi, yi. Okay, and don't worry about that in particular. That's just this is really just sort of manipulation of sort of that first expression there, and then this gives us the expression. This equals this same thing. I'm just going to write it now in matrix form. 1/2 theta transpose this guy 1 over rho plus 1 over sigma squared x transpose x. This term here is just our big matrix X times itself. Theta squared plus 1 over minus 2 over 2 sigma squared. It will be X transpose, or theta X transpose Y. Theta transpose this thing. Okay. Again, the details here aren't too important. Let's see, what does this boil down to? What this boils down to is the fact that when you write this all out, what you get for this expression, so when I simplify this sort of nasty expression here, what I get is I get a exponential of some quadratic function of theta. right? Where it looks something like this. It looks like some constant, I'll call it C3 now, times the exponential of 1/2 theta. This shouldn't be a 2 if I had a 1/2 there. Sorry. 1/2 theta transpose some matrix theta minus B transpose theta. It looks like that in my exponential form. And so the point now is I can now translate that to this form just by essentially doing a little bit of math here. Or not even math, just really manipulating that expression. So if I have some form like this, like the exponent of negative 1/2 theta transpose A theta plus B transpose theta, this is equal to the exponent of negative 1/2 theta minus mu transpose sigma inverse theta minus mu, where sigma is just equal to A inverse and mu is equal to sigma times B. Right? Because if I do this, then essentially I get a form here that cancels out. This term here will cancel out, and I'll get this expression from when I plug in to here. So that's all the trick is. I mean, it looks complicated, but it actually isn't. All we're doing here is just some basic algebraic manipulation of this expression in order to get it in a form that looks like the Gaussian density. It turns out once we've done that, we're actually done. Because we know that any distribution that has this form has to be a Gaussian distribution, and it has to have that mean and covariance. And so that really actually is the proof. It seems a little bit arbitrary, but that actually is the proof that the posterior distribution in the Bayesian linear regression setting is itself going to be a Gaussian. The way it comes up is you just write down the posterior, you simplify it until it looks like a Gaussian, and then it looks like a Gaussian, without the constant term. And then the constant term has to sort of make sense for it to be a distribution. So you found your distribution there. All right. No questions, I presume, right? It's easy. But it really, again, it looks kind of like it's arbitrary and kind of strange, but really it ends up having a very sort of simple form here. You're just manipulating the expression to look like a Gaussian. All right, so I wanted to have the actual proof. Again, probably the proof on the slides here is a lot more informative than the proof that I wrote out. But I wanted to have it just so you can see how one of these things worked. Because really this is actually an example of a much broader class of properties here called conjugate priors. So this is actually the important thing. This is actually the important part. Is just being a little familiar with this term here. So what a conjugate prior is, and this is sort of a really key idea in Bayesian statistics, is that what we're saying here is we're saying that our parameters have some distribution, which I'm going to call f, as a function of some hyperparameters. Right? And we're going to say that our data has, our data, given the hyperparameters, given the parameters theta, has some other distribution, g. And what we say is that f is a conjugate prior for g if f is a conjugate prior for g, then it turns out the posterior will have the same distribution as the prior. So the posterior, theta, given x, will have a distribution that's the same as the prior with just some different hyperparameters. And so in the case we saw before, what we were saying is that the normal distribution, at least the mean of the normal distribution, is actually what's called self-conjugate, and that it's its own conjugate. Because what we had was, we had the fact that f here was a normal distribution. So we're saying our prior distribution over our parameters was normal. Our posterior distribution of our data, given our parameters, was also normal. And what that implied, just algebraically before, was that our posterior of theta, given a distribution, has the same distribution, just with a different set of hyperparameters. In other words, a different mean and covariance. It wasn't the same mean and covariance as the prior, but it was still a normal distribution with some mean and some covariance that were determined by some. Oh, sorry, this is prime here. They were determined by some some function of the data. And so this is actually what it means to have a conjugate prior in this sort of in the general Bayesian sense. And there are many other examples than just the normals, but the normal is kind of one of the classical ones. The normal distribution is in fact, or at least the mean of the normal distribution is in fact self-conjugate. Yeah. Question?
You mentioned that it doesn't matter if G is also normal distribution.
So yes, here it does. So what this says, what we sort of proved before, is that the normal distribution is conjugate to the normal distribution. There are other distributions where the conjugate distribution is not the same as where f and g are different. In our case, f and g were actually the same thing. Though importantly, f was a distribution over the mean parameter of the distribution, not over the variance. So this is a distribution over the mean in our Bayesian linear regression setting, not the variance of that. Yeah?
What's alpha prime here?
It's just some different set of hyperparameters. So in this case before, alpha here would be 0 and rho I. That would be our parameters of our prior distribution. And obviously, the posterior does not have the same mean and covariance as our prior distribution. So what I'm writing here is kind of the generic form. It's just saying that the posterior, given the data, is the same class distributions, but it has different set of hyperparameters that govern it, right? So it's a new set of mean and covariances here. Really, maybe it would make more sense to say this is a function then of x and alpha, right? Because our new set of parameters for distribution can depend on our prior and on the data itself, but it will still be some set of parameters in that distribution that actually characterize our posterior.
And in general, is it easy to compute this alpha prime?
So in general, yes. For most conjugate prior pairs, actually every one that I know of, for most conjugate pairs, it's always kind of trivial. And in fact, the way they're kind of built is oftentimes you kind of build the prior distribution in a way such that the observation distribution, that is the probability of x given theta, is kind of an obvious addition to this. So again, it works the same way where you basically just find a new set of parameters that look like your old distribution, and that gives you a new set of parameters. And so here, really, the only hard part here was manipulating this into the form where it looked like a Gaussian, and that's typically what you do. You just manipulate the posterior to look like the prior distribution, and then you know what the parameters should be. So again, what we just saw is that the normal distribution is conjugate to the mean parameter for the normal distribution. If you wanted to have a prior on the variance of your normal distribution, that actually has another conjugate prior, which is called the inverse gamma distribution. So if I want to have let's see, I should trying to decide if I should write this or not. Maybe I won't write anything down because I might just get too involved here, and I have it on the next slide anyway. But maybe if you have if you have a normal distribution where you want to do Bayesian inference over both the mean and the variance of the distribution, you can apply a different conjugate prior to the variance parameter, which is called an inverse gamma distribution. what I'll say here is that while it's very useful, so this is a very key idea in Bayesian statistics. This case, because it's in some cases the only cases. These are the only cases where you really actually can compute those integrals there. In general, those are quite hard to compute for sort of general. If I have like a logistic regression model where I'm trying to compute the posterior over my parameters for a logistic model, you can't do anything like this. There's nothing that works exactly like this. So there are a lot of cases where this works, but there are also a lot of cases where you have to resort to things like sampling too. So we don't expect to have a closed form solution for what the posterior is, and we instead have to approximate the posterior by sampling. So both those things are actually quite common in it's common to use these when you can, but it's also common to not be able to use them. And so it's good to know sort of both situations. And I'll talk about the other situation in a second too, where you can't actually have a conjugate prior. All right, any more questions? So let me just go over one quick example. I'm actually going to hopefully redeem myself a little bit here because I forgot actually exactly what I was talking about in this past example, and I mentioned it, but now I was getting confused with the Bayesian version actually of change point detection. So I want to contrast two models now of traditional change point detection and Bayesian change point detection. So a change point detection model, again, remember, was a generative model. So now we're not, in this first one, we're not in the Bayesian land. We're actually in non-Bayesian land, at least in terms of the parameters. So T is a parameter of this first model, as are mu and sigma squared. And it's not one, it's typically one you would just find a point estimate for, not one which you would actually compute a distribution over. So here we have X being uniform, I'll just write like this, uniform 0, 1. This is the non-Bayesian version. And y given x is going to be equal to 1 distribution, normal mu1, sigma 1 squared, if x is less than t, and a different distribution otherwise. Mu2, sigma squared otherwise. Okay? And what this looks like, and t here is a threshold. I was getting confused with what t was last time, but t is a threshold. So everything, whenever x is below that threshold, you sample it from one normal distribution, otherwise sample it from another distribution. So what this looks like is the following. It looks like this, where this is x, this is y, and this is our parameter t here. And so every point below t would sort of come from one distribution, and every point after t would come from another distribution. Right? So that's sort of what samples from this distribution there would look like for a fixed parameter t, and also I should add sort of for a fixed parameters mu1, mu2. So I guess mu1 is here, and mu2 is here, with their own variance, sort of saying how spread out those things are. Okay? So again, our generative model is I sample first x uniformly at random in this space from between 0 and 1. I compare it if it's less than or greater equal to t. I sample y. If x is less than or equal to t, I sample y from one distribution, and then if x is greater than or equal to t or greater than t, I sample y from a different distribution. And the points you get look like this, right? So now I'm actually going to, so that's a pretty simple model. And if you wanted to estimate it from data, you might find point estimates for what the most likely set of x's there were, and you could write down the maximum likelihood estimate, and you could, actually it would be kind of hard in this case, but you could still do it. And that would be the sort of non-Bayesian version of this thing. So I want to describe now the Bayesian version of this problem. Maybe I'll use one of these other boards. Which is something called, this is a very simplified model. The real Bayesian change point detection is a little bit more complicated, but not that much more complicated, actually. Is there a eraser anywhere here? Am I sort of missing it? There was one on the floor. Okay. So in this Bayesian version, rather than have t, mu, and sigma be just parameters, they're in fact random variables. So that means we need to actually come up with a distribution that they're sampled from. So t here itself might be sampled from a uniform distribution in 0 or 1. That means we sample our first, before we sample data, we're first sampling our change point randomly in that interval. Then we sample our means. So So we sample mean mu1 and mu2 from normal with some mean 0, because this is the prior, so it's mean 0 in the prior, and say covariance nu squared. We sample sigma squared. Well, I assume we only have one sigma squared here rather than two of them, so we just have one sigma squared. We sample this from an inverse gamma. I mentioned that that was the conjugate prior of a normal distribution. We won't worry about what this is, but it has two hyperparameters, alpha and beta. And then we sample y. Then actually, we also sample x there. I haven't written that. But we sample x uniform 0 and 1. And we sample y given x, t, mu1, mu2, and sigma squared as the same as above, or whatever we have the same as above. So it's just those two cases as before. So what's important, I think, is to understand what this process looks like in some sense. So what I'm going to show next is I'm going to show you priors that I've drawn from this distribution here. So here, I'm drawing samples from the prior distribution here. And this is what they look like. So in this case, what they look like is I first randomly sample a change point for each one of these. So each one has a different change point. One's here, one's there, they're all different places. Then I randomly sample my two different means. So they could be one direction or the other. And then I randomly sample my variance, and I then sample a bunch of data points and sample the y's given that process as before. So what's sort of interesting here is not just this, because this is sort of, well, this is somewhat interesting, because what this is saying is that this type of data is what you can capture with this model, right? So the type of data that this model gives rise to is data that looks like this. It's data between 0 and 1 that has some change point in the middle somewhere, and that's sort of what this data looks like. And now what I can do, though, which is very nice, is I can basically run posterior inference to find, given some fixed data set, what's the distribution over over these variables, right? So now, given x and y, what's my distribution over t, mu, 1, mu 2, sigma, and sigma squared, given a bunch of x's and y's? Right? And this lets us essentially capture the uncertainty that we might have over our parameters given the data we've observed so far. And that looks like this. And here, what's sort of interesting is that we can no longer, in this model, compute that distribution analytically. There's no closed form for what this joint distribution over these things is given this. They're actually, it's going to be a joint distribution. They're all going to be dependent on each other. So I'm just showing like the 1D histograms here, but really this is forming a joint distribution in 4-dimensional space. And that's very sort of complicated. But what's nice about a lot of these Bayesian models is actually it's very easy still using techniques like Markov chain Monte Carlo. It's very easy to draw samples from this posterior distribution given our observations here. And they'll kind of like this. So my observation here's on the left. That's saying that I observed this data. And I am then going to come up with a distribution, here plotted with histograms, which are imperfect because this is really a multivariate distribution. But here plotted with histograms over what I think those parameters are. And what's nice here is this sort of captures not just the sort of single best estimate we have over these parameters, but it captures sort of the fact that they may lie in a whole range, right? It actually may be, we're not really, for example, in this data, the change point that is actually the generated this data from is t is 0.5. So it's everything less than 0.5 is one thing, more is that. But the data actually has no values between around 0.44 and just over 0.5. So what you actually see in the posterior is that the posterior over t is actually pretty much uniform between these two values, because there's nothing in the data to actually imply where in that range it really lies, right? So the posterior is kind of flat over this. Similarly, I think I used for both of them a mean of 1 and -1, but it's not completely clear from the data that we've observed that we're definitely at 1 and -1. In fact, there's actually quite a bit of variance about where around that range we could really have that mean. And these samples from the posterior capture the fact that we do have some uncertainty there. We actually even have even more uncertainty in the variance parameter. So tau is actually the, did I use, oh, I thought I used nu, but I guess I used tau in the code here. Tau is would be the hyperparameter of, it would be one of the hyperparameters rather of, or it's this thing. I think it may be this thing, the inverse of that thing. I think tau here is 1 over this thing. But tau here would essentially capture the fact that we are also uncertain in our estimate of the variance of this distribution. So we also have some uncertainty over how much sort of we really believe there to be, where we think our real estimate of our parameter sigma squared is. And so the big kind of message from all of this is that when you have a finite number of observations that you actually see, if in the limit of infinite data, essentially these problems go away because you get more and more certain in all your estimates, and for the most part these would all collapse to a single point anyway if your data really is generated from a single point estimate. But when you have a finite amount of data, your data does not actually tell you. I mean, one point estimate might look like the best one, by maximum likelihood, but really there's a whole range of possible values that these things could take on. And maximum likelihood estimation does not really tell you whether, all values around there are equally good, or whether there's sort of one estimate that's sort of the peak distribution that everything else around it has very low probability. And so what these Bayesian tools let you do is they let you actually quantify the actual shape of the uncertainty around your parameters and understand, when you say this is my estimate of my parameters, or this is where I believe my parameters are, it lets you sort of specify both how confident you are in that to a certain extent and sort of how much uncertainty you think you actually have around those parameters. So that can be a very useful and valuable thing. And the other point, as I mentioned before, is that when you want to use it to make predictions, that will also actually translate into more or less uncertainty in your predictions that you make as well, because you have uncertainty over your parameters. And so this is sort of the advantage of Bayesian statistics that kind of give a unified framework for handling all this amount of uncertainty. The nice thing I'll say too, and we're not going to cover this in class, but for those that are interested, this is all very easy to do programmatically. So there exists this set of tools called probabilistic programming tools, and they basically let you specify distributions more or less in the form like you see here. Like you can basically just write that t is normal with this, mu1 are normal with, or t is uniform with that, this is this, and then it lets you say, okay, I'm going to observe these two things, what's my posterior over my other parameters, and lets you essentially compute a very, very good version of Metropolis Hastings specialized to this problem that will give you sort of samples from your distribution over your posterior. There's also versions that work with what's called variational inference. So there's a lot of really powerful tools that can be brought to bear. And so just like you have tools like TensorFlow or Torch and these things that work really well for deep network modeling. Similarly, for generative models now, you have a powerful set of tools that let you essentially just write your model down and apply inference. So we're not gonna cover those, but if you want to check them out, probably Stan is the most popular one. It's written by some people at Columbia University. PyMC is another very popular one. Edward is actually one tuned a little bit for deep generative models, which we'll talk about next very, very briefly. But these are all really powerful tools because they let you essentially experiment with the mechanics of these Bayesian models without having to generate your own Gibbs sampler or your own Metropolis Hastings sampler every time you want to sample from some new distribution. All right. So in the 15 minutes I have left, I do want to cover just the high-level overview of a few. I'm not going to write anything for this, and I'm going to show some pretty pictures at the end, as I always do with deep learning, because it's so amenable to that. But first, are there any questions? I also skipped the poll today because I wanted to get through this all. So that means you're here for no reason in class. Sorry to break it. I'm telling you this now, not at the beginning, because people might start sneaking out. And there are some pretty pictures coming at the end, so maybe you'll stay for those, if nothing else. All right. So the last thing I want to mention, this is going to be very, very brief, because as I said, I wanted to cover those things because there's other elements. covered, I think, a lot more of a core of what people think about when you think about probabilistic modeling in AI. But given that this course is trying to at least expose you to some of the latest sort of methodologies in AI, I want to briefly mention the fact that there is a whole sort of literature on combining the last two things we've talked about in class here, namely deep learning and probabilistic modeling. So the idea here is, what probabilistic models are great and deep learning is great, so we're just going to combine them on what could possibly be better than that. But to qualify a few things, first of all, this is not a new idea. So these ideas go back until at least the 80s, probably earlier than that. Since people were doing neural networks in the first place, people have been developing probabilistic takes on them. They've had very different styles. We're going to follow kind of one of those lines of work. And I'm basically going to trace through the origins and the basic setups of three types of models. The first is going to be something called a restricted Boltzmann machine, which is an undirected graphical model that was very popular in deep learning, or rather deep extensions of it have become very popular in deep learning. They actually are partly due to the resurgence, or partly responsible for the resurgence of interest in deep learning, historically speaking at least. And then I want to talk about a little tweak on this called deep directed models, of which there are many types, but amongst others there are things called variational autoencoders. There's also something called a Helmholtz machine, but we won't actually worry about those distinctions there. And then I want to move to the last one, which are actually an even kind of tweak of that thing called generative adversarial networks. And these last ones are very, very popular right now. I think actually a lot of work that came out in the last year or so focuses on these deep generative networks. And I want to go through at least what these are conceptually, not with any sort of, with very minimal math here. I want to just talk about kind of the structure of these models and what they're actually doing. So to start with, I want to mention what a restricted Boltzmann machine is. So we've talked mostly about directed graphical models in this course, things like Bayesian networks or generative models. You can also define what are called undirected graphical models that just give, basically where all you're doing here essentially is saying that my distribution is proportional to some function of all my variables. And in this case, Boltzmann machines essentially give a distribution over two sets of variables. The x variables, which are the observable ones, and the z variables, which are the hidden ones. And they give a distribution which is a graphical model, but it has no real arrows between them because there's no real notion of direction between them. It just says that the probability of both those things is proportional to some function, some linear functions of both the x and the z variables, and then some sort of bilinear function x transpose wz in both those two sets of variables. And by the way, the reason why this is restricted is if you think about the connections this thing can have, it can have dependencies between the x variables and the z variables. That comes from that first term there. And it can have individual potentials on each x variable and each z variable. Those come from the second terms there. But there's no term that can involve two x variables or two z variables. This actually makes inference much easier, or relatively easier in these models, for a reason we'll mention in a second. But basically, this ascribes a distribution over both these things. And you should think of these mainly, I mean, for a long time, there have been extensions, but for a long time, these were just applied to Bernoulli random variables. So you should think of at least these things being binary, every x and z here being binary. And it won't always be that way going forward in a lot of these sort of actual implementations, but it's a reasonable way to think about them, at least for getting started. So how do we train these things? Well, training here actually involves just maximum likelihood estimation. We just want to maximize the probability of some observed data. But what this involves is, in order to compute this probability here, the probability of x, we have to, for each variable, sum over all possible assignments of z, which is kind of annoying because there are an exponential number of these things. And so it turns out we have to essentially run an inference procedure to actually compute even what this thing is, what the likelihood function is that we want to optimize. And we have to run an inference procedure to compute a gradient of this likelihood function. So we won't get into how you do that. It's actually not very complicated. But you can tune these things. The only thing I'll say is that training these things involves running an inference procedure in order to get a distribution over which you need that you need over your hidden variables in order to actually train this thing. It's also the case that actually sampling from the distribution requires that you run something like a MCMC method, right? So there's no obvious way when you have a distribution like this to just say generate a sample from this data, right? even over both x and z, right? I can't really do that. There's no sort of generative process where I know my first thing to sample from like a normal distribution, I know my second thing. It's just the joint distribution over both of them. How do I sample from that? So it turns out that sampling also will involve something like Metropolis Hastings. But it actually turns out that for these models, there's a very efficient way of doing this, involving what really breaks down to a block Gibbs sampling, where essentially it's the case that if you fix the z layer there, it's pretty easy to sample a set of x's. And then if you fix the x's, it's pretty easy to sample from z's. That's because once you fix one of them, and you can see this just from the sort of definition of the distribution, once you fix one of them, the remaining things are all independent. So given z, actually my probability of over x is just the product of probabilities all for all my xi's, so I can easily sample from that. Because they're just binary variables here, so I just compute the probability of each one and sample from that. And the same happens with the other one. So what this leads to is it's a very easy way to compute Gibbs sampling here. I just fix one layer, sample from the other, fix that layer, sample from the other, and I repeat this process, and pretty soon I have samples from my distribution here. But even that has already, I mean, remember Gibbs sampling already is this Metropolis Hastings type algorithm, and we're running Gibbs sampling just to sample a single sample from this distribution here. So I'm actually not going to compare sort of the pros and cons of all these things. I'm just going to say that this will require some effort to do both sampling and training, because training and sampling both require running inference. If we accept that, though, these actually can be very powerful models. And they've been extended to the deep setting, where instead of having just one layer of hidden variables, we actually have multiple layers. So a deep RBM, restricted Boltzmann machine, is a very common model. This is actually, as I said, one of the models that really kind of, Jeff Hinton's work in the late second half of the 2000s really kind of laid the foundation, I think, for the resurgence of deep learning as an area of interest. Most people, I will say, have sort of gravitated towards more generic neural network models than these things, but there's still a very active set of research kind of thinking about probabilistic models for these things. Ruslan, for example, here in MLD is actually one of the kind of stars in this field and has a lot of really amazing results with RBMs or similar models. So we can stack these things, but the idea here is that still all the problems before persist. So still training them is hard because we have to essentially run inference now, and now actually inference is even harder, right? So what we have to do to solve inference now is like some sort of like layer-wise sampling, where we first sample one layer, then the next one, then the next one. It gets really hard to do these things. Kind of actually, they get kind of nasty to do, but you can still do them. But because they're kind of annoying in some ways, people have thought about other models that you can do that actually sort of prescribe maybe things that are a little bit easier in some aspects than RBMs. And I should say all this, by the way, this is sort of my take on the whole field. I think if you talk with Ruslan, he'd give you a very different take. So this is still largely a matter of interpretation about sort of how you view some models being easier or less easy than others, I think. So just let me preface that as well. Okay, so the problem here in some sense is that the nature of this model made it hard to even generate samples from this distribution, right? It's actually kind of tricky to even do that. And so because of this, a lot of people moved to directed models instead of undirected models. And so instead of having this network what we had before, where all the edges essentially were undirected, what that means is that they're just defining a joint distribution over all these things. And the natural extension is just you have that same term for each model for each layer individually, now each pair of layers individually. Instead of that, you actually now have a directed model where you start at the top. The other thing I should add is for some reason these models, generative models, are always drawn top to bottom instead of left to right. I don't know why, but I'm going to follow that notation. That's just how they're always drawn. But instead of sort of thinking about these as all being undirected connections, we think of them as actually being a generative process that starts at the very top layer and proceeds down. And the nice thing here, and this is sort of actually the opposite direction of arrows as you think of in a normal network, right? In a normal network, you have your input and then you kind of do a feed-forward process. Here you actually have sort of the top layer being the thing that you specify, and then once you have the top layer, you just sample to go down from that. What's nice here is that these types of models allow for efficient sampling. So if I impose some pretty simple distribution over my top layer, say my top layer is just all 0.5 on all the Bernoulli random variables, then it actually becomes quite, and I have a sort of a functional form for each of my conditional distributions. Then, if I specify this in the right way, I actually can just easily sample a set of outputs, or a set of really all my variables, but including my outputs, in kind of the full Bayesian network sense, right? We remember that when we have a Bayesian network, it's pretty easy to draw samples from that, because I can just start at my first variable and sample and sort of sample downward, right? And I can do that here. So essentially, what I can do here is I can just sample my first layer, use my first layer to sample my second layer. I'm actually, remember, my top layer, sample the next top layer, the next one, and finally I sample my observable variables, and that's my output of my system. So I can now draw samples from this model efficiently. And there have been a lot of variants on this model. The problem, of course, is that maximum likelihood estimation, or training my parameters for this model, which are all the sort of conditional distributions here, is still hard, because when I want to run inference, or when I want to run sort of conditional or posterior inference, what it's saying is that I still have some observed data that I'm observing, and I want to find parameters that fit that. And so this is, again, that same case of the Bayesian network where I observe the last element, and I want to sample from the previous ones. And even though I can sample from the prior distribution, it's very hard to sample from that posterior. And so training these things is still quite difficult. And in fact, a lot of the work on this, and a lot of the different models you'll see, amongst them the names like things like variational autoencoders or Helmholtz machines, they are all different ways of sort of approximating this training objective here, because you can't actually do this very easily. You need some approximation here, and that's hard to get at, and so you need to sort of somehow approximate this, and that's what these things like conditional or variational autoencoders actually do, if you hear about those names. But the advantage here is that once you've trained the model, we now have a very efficient way to sample from it, right? So I can train my model. That's maybe hard. It takes a long time. I have to run some very complex inference routine. But once I've trained it, I can easily generate samples from it, at least samples from the raw X's. The last thing that kind of has happened, yeah, question? Yeah, I'm saying that we essentially have all those terms up there, all those p terms. I'm saying that given parameters, we have a functional form for them that we can sample from. Now, the difficulty here is the fact that we have to still essentially sum over this z, or in other words, perform some kind of sampling over the z, which is actually very hard, even if you have a functional form going forward. This is the Bayesian problem we had before, of when you observe the last element, it's still hard to sample from the previous ones. So training still involves some complex inference here, whereas sampling, from the default model, given some parameters, is not very hard.
You would still need to sample just the first layer, right?
To compute maximum likelihood estimation, no, you have to sample from the posterior given some observed data. Remember, because maximum likelihood estimation says I'm given some data, find my best parameters that could have led to that data. That's not easy to do, because there you still need to compute inference given that observed sample. And so people have been thinking about other ways of training models like this that don't involve such complex inference. And one really popular one right now is something called a generative adversarial network. So this network is still the same form as before. It's a generative network that sort of proceeds from the top and then goes downward. But instead of training it using maximum likelihood estimation, we do something actually very different. So instead, we actually say, look, I'm not going to try to do maximum likelihood estimation in the normal way. What I'm going to do instead is I'm going to try to build a separate class. In some sense, conceptually, my samples are good, right? My samples from my model are good if they look a lot like the samples from my data, right? That would make them good. And so the way that we quantify this is we say, I'm going to try to train a classifier to tell apart samples from my model versus samples from the actual data. This is actually a very clever idea. And you formulate it as a minimax game. This is actually very, very recent, too. This is work by Ian Goodfellow in 2014, and it really only became practical starting last year. Less than a year ago, the paper came out now that kind of made this thing practical, and there have been since then, probably 20 papers talking about this stuff, of some of which I'll show in a second. But the idea is you train this thing, and this has its own problems, by the way, in training. It's also quite finicky in a lot of ways, but you don't need to run inference when you train. So you have a generative model where you actually do not need to run inference in the normal sense in order to find the estimates of the parameters for the model. And so I'm over time here, so rather than sort of dwell too much on this, I just want to show some examples of how these things look like. So this is an example of a model trained to generate bedrooms. So it was trained to generate it was trained on pictures of bedrooms and houses, and then it was just asked to just generate samples. And if you should look close at these things, they look ridiculous. They're all sort of nonsensical. But if you look not too closely, they all look like reasonable bedrooms. Right? They have things that kind of look like beds. They look like other things that are maybe like windows, stuff like that. And they look, and there's no image like this in the training set for all of these things. These are just brand new images that the model has hypothesized given one of these generative adversarial networks. In fact, one of the most compelling applications I've seen of this is on this data. So this is almost getting a little bit spooky how well this works. But what this is data. So I showed you before data going from a picture to a caption. This is the reverse process of that. So this is actually just given the text caption, the system trains actually a conditional generative network. So actually it's conditioned on some text. But conditioned on this text, it generates an image from this text. And so the top left there says, for example, this bird is red and brown in color with a stubby beak. And from that, it generated that picture there, which is a red and brown bird with a stubby beak. Now, I should clarify, this data set is a data set just of birds. So it's not like you have the universe of all things and it can describe anything. It definitely knows about birds and like what the variance of birds looks like. But it's still pretty incredible. I mean, I think even 2 years ago, this paper is now probably 6 months or so old. But even a few years ago, there was nothing that could do anything like this, right? So we could not take text and hypothesize, synthesize images from this text. And really, almost every day, there was a recent one of trying to color photos, like take a photo in the daytime, give it an image of a photo in the nighttime, and actually translate between those two things. So it's actually really incredible, sort of the progress on these things. And while I highlight a lot of this is kind of the general progress of deep learning, it really is these generative models in a lot of cases and these generative adversarial networks that have been able to accomplish that. So hopefully, if nothing else, this will be an impetus to read more about these things because they're really kind of advancing AI almost at a scary rate in some cases. I mean, I think what's coming out every day is really, really impressive. So, all right. I think we're taking a big step next time. So next time, Ariel will be teaching about game theory. So this sort of concludes our probabilistic modeling and deep learning section, and you'll have very different stuff going forward. So see everyone soon.